EX129 as application of exercise. $126. There we talk about commutativity of limits with limits, limit commutativity with limit. Recall that we proved that by first prove this in the category of set, and then by unit embedding we turn the question of general category into the question about the category of set. So the exercise is prove Z hat is isomorphic to product of ZP. So let's start. So the Z hat is by definition inverse limit over n for Z mod n. So let's recall that the transition morphisms, the diagram is defined the embedding category as, so it's Zn, there exists a map from n to m, mapping x to x bar if m divides n. Otherwise we don't define there is transition map. So you only have to check those. And then Chinese remainder theorem, this could be further write as Z mod some p power. So let me use a very clever notation. Let's call it EPN. EPN to define, so there are two index p and n. EPN is to define the index. EPN is to define the integer power of p in the unique factorization of n, right, into p powers. Okay, and now by using this we can rewrite our Z hat as inverse limit over n, and then product, sorry, by Chinese remainder theorem, this is a product of Z mod p EPN for p. And then now what is left is to say that this when this, we're going to let firstly exercise 127 126 to exchange the order of limit and product. This is very clever way, because if you want to put n here, p divides n such that PEP, then you will find this is very difficult to, you're kind of using double index for this. But if you just write EPN here, then you allowing any prime numbers here, and then you could very easily commute those two. And now let's focus on this. I'm claiming that this is just ZP and finish the proof why this is. So the taking inverse limit of n, recall that this is actually, we're only looking at those transition morphisms with divisibility. So if m divides n, then obviously EPM would be smaller than EPN, and then the transition maps there would correspond to let's say EPN just by reduction, projection. That's the transition map. Right, that corresponds to transition maps of ZP limit. So this could probably become the same, but then this will be the identity map, and then you can take in the limit. If there is a two-term, this copy of term that doesn't influence the limit. Let me just put a remark. So notice that. So just because this is sometimes very confusing, if you are thinking of this as subset or submodule of product ring, right, then and then you prove that this is actually the same as product of ZP. Right, any element here could be written as x0, x1. Let me see. I'd rather say n bigger or equal than 2. And so an element could be written as a tuple here, right? So let me record x2, x3. So I just want to kind of connect these two things, how to embed this there, right? For example, if you take identity in Z2, this corresponds to 1, 1, 1 in the product of Z mod 2, Z mod 2 square, etc. And then how do you map it there? The point is that this should be mapped to 1, 0. To be more precise, let me write 1 mod 2, 0 mod 3, 1 mod 4, 0 mod 5, and then 1 mod 6. So this is what happens very strange, because here there's no terms lines in mod 6, but why here I have to put 1 mod 6? It's because Z mod 6 is isomorphic Z mod 2, Z mod 3 by Chinese remainder theorem, and so, and also under the transition maps here. Imagine you have this Z mod 6, sorry, in the diagram here, imagine you have on the one hand this Z hand, and then here Z mod 2, Z mod 3, Z mod 6, right? So you have maps x map to x bar, and so any element here, this is mapped to some position x. How do I call this? Let me just put the subindex x6 here, and then this is telling you that no matter how this element is, it should satisfy that x2 should equals to x6 modulo 2. Similarly, x3 should equal to x6 modulo 3. And then this is exactly telling you that if you already nodes x2 and x6, x3 position, then your x6 position is determined by the Chinese remainder theorem, because the two product of these three is the 6, right? For this reason, if you're 0 mod 3, 1 mod 2, then you must be 1 mod 6. And actually you are, what you are doing is inside here you're doing z mod 2, z mod 3, z mod 2 square, z mod 5, z mod 6 is again z mod 2, z mod 3, but this is some information duplicated, because once you know what is here, we will know this. And then z mod 7, and finally you will see that what you are left is only the prime powers, and then you just collect all those, and I said z mod 10 there will be useless, because this is z mod 2, z mod 5, and it's uniquely determined by what is already there. So finally you just collect all those, and it gives you z2, z3, right? That the fact that limit commutes is kind of telling you that you could reorder them.